translate or transform any normal distribution into a Z distribution. Z distribution is a standard normal distribution. What's the difference between any normal distribution and standard normal distribution? Anybody? What do you mean by standard normal? Exactly, yeah. It's exactly one of the normal distribution. The only difference is standard deviation is 1 and the mean is 0, right? That's what we call standard normal distribution or Z distribution. And I explained why we need to translate or transform normal distribution into a Z distribution, because ultimately we are going to calculate the probability as the area under the curve between any number A and B, okay? And the way you do it is you use integral calculus from A to B, and you know that PDF, probability density function of normal distribution, as I showed you last class, right here, right? So this is the PDF, what we call probability density function of the normal distribution. In other words, that's the equation of this curve. Equation of this curve, right? So probability, it can be calculated as an area under the curve between certain numbers. And I already told you last class, what's the probability of single number? X equals A. It's 0, okay? So we will, when we are dealing with any continuous probability, continuous variable, okay, we will calculate the probability as an area under the curve between certain numbers, okay? Well, since probability of A is 0 and probability of B is 0, there is no difference between this expression and this expression, right? So whether you include the equal or not doesn't make any difference, okay? That's another thing you have to understand, okay? So whatever the PDF you have here, right, and dx, okay, then that's how they calculated the probability of all the values. If you look at z-score, z-table, let me pull up one thing here. I just copied the table E.2 from the back of your textbook, okay? So this table, for example, gives the area, cumulative area between negative infinity and z, any particular z-score, right? So if you have, say, negative 3.8, for example, right? If z happens to be negative 3.8, then you can find the probability this area is 0.00007. It's a very small number. So the negative 3.8 would be way out here to the left side, left end, okay? That's why the area is so small, right? If you get down to 0.0, if the z-score happens to be 0.0, that means we are right at the center, okay? Then the area or probability that the z-score will be less than 0 will be exactly 1/2, 0.5, okay? So that's how you use the z-table, right? So let's say negative 1.28, suppose, right? You calculated any number, let's say, converted any random variable x into z-score using this formula, came out to be negative 1.28, right? Can you find the z-score? I mean, the probability that z will be less than or equal to negative 1.28? from this? If you have a good eye, I guess. Let me make it a little larger here. Well, you know, this is 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have to go to the last column here. Okay, so negative 1.28 would be 0.1003. In other words, 0.1 almost. Okay, so you can say, right? So here, z-score, if the z-score happens in negative 1.28, this area is 0.1. Okay? Does it make sense? And that's how you use z-table. So, as I explained, the statisticians already spent so much time constructing this z-table. Okay? This is only half of the z-table. If you go to the next page, then you have the other side, right? In case z value happens to be positive, starting from 0, 0.1, 0.2, and so on, right? So we know everything about z distribution or z table. So once we convert x values into z-score, we can calculate the probability, right? That's why we need to translate or transform x values into z value, okay? All right, as we've just talked about, distribution is symmetric. So left half is 0.5, and the other half of the probabilities are distributed on the right-hand side, okay? So make sure you understand that idea. The entire area under the curve, in other words, if you have any random variable x that will be normally distributed, okay, then probability that it will be from negative infinity to positive infinity will be 1. In other words, all possibility, when you count all possibility, the probability is 1, okay? This is an obvious concept that we all learned already. Okay, so these a few slides explain how to use z-table. So we can go very quickly here. For example, after the calculation, you came up with a z-score of 2.0, right? And so we have on the right-hand side here, okay? And what's the probability that z-score will be less than 2? Well, you can go to the z-table again and look for 2.0 right here, okay? And 2.0 is 2.00 if you go one more digit, right? So that's 0.9772. You can find it exactly. Or in case you were given only this table, the negative side, then still you have no problem finding that number, right? Because we know that the distribution is symmetric, right? This side is equal to this side, right? So if this is 0.9772, okay? And let's say that was 2.0, and we are looking for this area, right? But you were given only this table. What can you do? Can you still find this number, right? When you're given the table for only this side? Okay, how can you do that? I'm sorry, what? 0.5? Add 0.5 to what? Okay, well, let me rephrase my question here, right? The question is, we are looking for the probability that z will be less than 2.0, okay? And if you were given the table, second table, which gives the positive value of 2.0, we can find out this, this entire area was 0.9772, okay? But suppose you were given the first table, right? In the first table, you were given only negative z-scores, right? So can you still use it to answer the question? What value? Okay, because the idea is if this is 2.0, right, there is a negative 2.0, okay? And you can find the value which is less than 2.0. Okay, this area. Okay, so you know that if you subtract this area, the rest of the entire distribution right, that will be the same as the yellow shaded area in the first time, right? Because it is symmetric, right? So you can do the other way around. So you use this table and look for the value of negative 2.0, and that's 0.0228, right? So you can subtract 0.0228 from 1, right? Then you get the same answer. Am I making sense? So you have to use the fact that the distribution is symmetric, and you can be provided only one table, and you can still answer all the questions. All right. Well, we're going to have some exercise on this later. Okay. So, all right. So that's this was an easy question, right? Now, let's say we start from a problem which deals with any normal, regular, usual normal distribution instead of standard normal distribution. So in this setup, we were given an x value, any random variable which is normally distributed, with a mean value of 18 and the standard deviation of 5. Okay? And I think if you remember this setup, this question is about downloading speed. And x is number of seconds it takes to download any information. Okay? So the internet service provider is telling that our speed is very fast. So on average, it takes only 18 seconds to download, I guess, huge file, maybe a movie or something, right? And what is the probability that it'll take 18.6 seconds or less? Okay? That's the setup, right? So probability that x will be less than 18.6. In order to find that probability, we have to convert it into z-score, of course, because we don't know anything about this x variable. There can be thousands and millions of different normal distribution, but we don't have all the tables for each of those normal distributions. But we can convert it. Once we convert it into standard normal distribution, then we can use z table, okay? So you know how to convert it. You subtract 8.6 minus 18, and then divide by standard deviation. So move the center, and then compress the distribution, okay? Obviously, if you have standard deviation of 5 in any normal distribution, that is 5 times wider than standard normal distribution, okay? So that's why we divide it by 5. So that 18.6 in this x scale converts into 0.12 in z scale, okay? And then you can go to the z table and look for z-score of 0.12. What is that? You see that number? 0.12. What's that number? right, it's right here, right? 0.12 is 0.5478, right? So that's the cumulative probability. Remember, this table gives the area starting from the negative infinity to that particular z-score, okay? So that whole area is 0.5478, slightly larger than 0.5, okay? So, well, that makes sense, because if z-score is 0.12, that's slightly to the right of 0, right? You know, the entire left area is 0.5, right? So that's a little bit larger than 0.5, okay? So from the table, we find the value is 0.5478, all right? Any question about how to find normal probability? How to use z-table? All right? And again, we will have some more exercise later. All right, empirical rules is very interesting, very popular concept, very frequently used concept, right? It's just the characteristic of normal distribution, okay? You probably noticed that I'm staying here in the center today. I examined the previous recording, and I found out when I move around, the screen trembles and it doesn't show the entire screen. And when I use the laser pointer, it doesn't show up on the screen. Okay? Because you can watch this entire computer screen. If you tried, right? There are two sections, two screens, two windows. Okay, one window shows this computer file exactly. The other window shows me. But if I use laser pointer, it doesn't show in any of them, right? So I'm trying to use this mouse, and you can see what I'm pointing, right? All right. So here we have a normal distribution, and one distinctive nature or characteristic of normal distribution is if you have one standard deviation area. So from the mean, you go to the right by one standard deviation, to the left by one standard deviation. Then this section, this middle section, right, between these two dotted lines, cover about 68%, approximately 68% of the total distribution. That's one typical characteristic of normal distribution. Okay? If you go one more standard deviation, two standard deviation to the right and to the left, okay, then there's two standard deviation area. So from the center, we have one standard deviation. That's 68%. Okay? If you extend it to about two standard deviation, another sigma here, okay, then that area covers about 95% or 95.5% of all the distribution, right? If you extend it to three standard deviation area, six sigma, okay? So 1, 2, 3, 4, 5, 6 sigma area, right? Then it covers 99.7%, almost 100% of the distribution, right? So in other words, if any variable is normally distributed, then almost 100%, 99.7% of the times, you will find that number between mu minus negative 3 and mu plus positive 3, plus 3. Mu minus 3 sigmas, mu plus 3 sigma. Okay? So this 6 sigma areas cover almost all of them. Okay? So if you have any particular number that is outside, then we typically consider those numbers outlier, extremely small, extremely large number, unusual observation. So that's empirical rule. Okay? So if you want to find out whether any distribution or any random variable is normally distributed, then you can use this criteria. Okay? When we find out the 1 sigma area from the mean to the right and left, do we find about 68% or maybe 70%, right? In reality, it's extremely unlikely that you will find exactly 68%, right? But somewhere between 65 and 70% of the distribution, if that's found within one standard deviation area, well, that qualifies, it satisfies at least one condition for normal distribution, okay? And so on. So here's an application. You don't have this slide in your note. I just included it as a presentation purpose, okay? If you work for a company, there are quality control people, okay? And this control chart is very important tool in quality control concept, okay? So suppose, I think this example is for bottle filling. Suppose there's a bottling company, fills them beverages in a bottle, 16-ounce bottle, okay? So it's supposed to be 16 ounces, okay? But on average, this black line, thick black line here is CL. CL stands for center line. Center line is the average of the sample means, okay? And what that means is when you select many different samples, I believe this quality control people will probably take the sample every hour to make sure the machine is working fine, okay? So this is sort of grand mean of the means, okay? So every hour maybe they elect, randomly select about 10 bottles, okay? And measure the exact content of each bottle, okay? And calculate the sample mean of those 10 bottles, okay? And you do that for 24 hours, right? 365 days, right? So there are so many samples, right? But center line will be the grand mean of all the samples that you've taken, right? In other words, the center line should be actually the target value, okay? So why is target value slightly less than 16 ounce when the bottle says 16 ounce? Shouldn't it be 16 ounce? Well, there may be some conditions. Maybe they need to include some gas or whatever, right? So maybe the actual content is 15.95 ounces instead of 16 ounces. Anyway, so let's consider that black line as the target line, okay? Then there is UCL and LCL, okay? In any control chart. UCL stands for upper control limit, and LCL stands for lower control limit, okay? And it's simply CL minus 2 sigma. Lower control limit is CL minus 2 sigma, okay? And the upper control limit is CL plus 2 sigma, okay? So every hour, they take a sample. So apparently in the first time, the sample, you collected 10 bottles randomly and measured the exact contents. Then average of those 10 bottles were 15.9 ounces. The second time, next hour, you selected another 10 bottles, okay? Came out to be 16 ounces, and so on, okay? Well, you have to understand this is a random process. And in reality, even if you use the same machine, right? The sample means will be all slightly different, right? And we don't understand. We cannot explain. That's what we mean by randomness. In statistics, when we say randomness, what that means is simply we can't explain. Right? We don't know why we have this variability. The reason is there are so many factors in our life, right? Maybe that particular second, the Earth spun a little bit slowly. Right? Maybe there was some sun flare, right? and affected the electromagnetic field, and so the power in this company was slightly lower than usual, right? There are thousands and millions of possible reasons, okay? So even if you use very good machine and same process, right? Typically you see these very minor random fluctuations, okay? But the question is whether what we need to find out is whether the machine is working fine or machine has a problem. Okay? If machine really has a problem, then we have to shut down and adjust the whole process, right? Or fix them. Okay, right? But somehow, if one sample goes above UCL or below LCL, right? Then you got a problem, right? Because that's outside the normal randomness. Okay? In other words, considering the empirical rules, okay? How likely is it to happen? In other words, if the machine is working fine, in other words, if really average of all the sample means still 16.95, right? How likely is it that you will have above this point, above this line? How many times will that happen if you collect the sample 100 times? About 5 times, right? Why? Well, no, actually less, 2.5 times. Why? Because according to the empirical rule, you know that within 2 standard deviation area, we have 95% of observation, right? So probability that it will exceed this 2 sigma value is 2.5%. Probability that it will be lower than this 2 sigma value is another 2.5%, right? So if the machine is working fine, right? And if this the quantities, the amount of liquid in the bottle is normally distributed, right? Then if you collect the sample 100 times, then about 2.5 times you can get extremely large value. About 2.5 times you can get extremely small value, or extremely means 2 standard deviation values, okay? That's the idea of control chart, right? So this is just a basic concept of control chart. You have to learn if you want to really understand the control chart concept. There's a little more complication here. And depending on what process you use, what kind of product you produce, there will be some minor variation in the control chart. And does that mean if you have that number above UCL, does that mean you have to shut down the machine immediately? Not really, right? You have to consider other factors. The sample size matters, and so on. Okay? All right. Here's another important concept, but you know, it's sometimes instead of finding the probability based on X value, we want to find the X value based on the probability. Okay? So in this, using the previous example, in this case, this company claims that on average their download speed is 18 seconds. Okay? And previously we asked, well, what's the probability that it will take less than 18.6 seconds, right? But this time, they want to find out, well, about 20% of the cases, they can even download it even faster than 18 seconds, right? What is that exact number of seconds here, right? That will give 20% of probability, 20% of the cases, okay? You know, you can imagine many different cases. Suppose you are applying for job and you take some exams, some civil servant exam or TOEIC or whatever, right, exam, right? And suppose you want to belong to top 10%, right? So if you want to belong to top 10%, what's the required score, right? If the scores are normally distributed, right? So we're talking about out of the normal distribution, we want to find out this particular X value that produces top 10%. Okay? So that's the reverse case. Well, it's a very simple concept, right? Because you know how to do it. Z-score is X minus mu over sigma. Okay? But this time we know the Z-score. We can find the Z-score because we know the probability, right? So you can convert this back to X is mu plus Z times sigma from this formula. Okay? So as long as you know the mean and standard deviation and the probability, based on the probability you can find the Z-score, right? And then you can find X value. Okay? Well, here's an example. So using that particular example, you want to find out that particular X score, which is unknown at this point, right? Which has 20% area to the left, right? So you can go to Z table. Let's go to the first table here. And this time you have to work from inside out, right? In the previous example, we knew the Z-score. So we located the Z-score and located the probability here, right? But this time we know the probability. Probability is 0.2. So from this table, you have to locate 0.2. Well, as you see here, it starts from a very extremely small number. And as you go down, it becomes larger and larger. Here's 2.119. And, okay. And here's 0.16, 2.005. Okay. So in all likelihood, you're not going to find exactly 2.000. I mean 0.2000. So you have to choose the closest value, right? Where is the closest value? Here's 0.2005. Here's 0.1977. Which one is closer to 0.2? This one, right? Because this is 0005 away. This is what? 0023 away. Okay? So you have to choose. Some statistics teachers ask students to interpolate to come up with the exact number, right? Somewhere here, right? But I'm not going to do that. Right? You can just choose the closest number. Okay? So here's 0.2005. And the Z-score, that gives you 0.2005 area to the left, is negative 0.81234, right? Negative 0.84, right? So you come up with a Z-score of negative 0.84, okay? So that's how they came up with the negative 0.84, right? And once you find the Z-score, you can just work your way back to X value, right? So 18 plus negative 0.84 times 5. So come up with 13.8, right? So in the original X scale, this value was what? What was it? 13.8, okay? So we came up with, if you have 13.8, so you can say what this company can claim is, you know, our internet speed is so fast that when you download the entire movie, it takes, what, 18 seconds or whatever, right? But even some cases, even in 20% of the cases, it takes less than or equal to 13.8 seconds. Okay? That's how you can use that result, 13.8 seconds. Does it make sense? Okay? Simple, right? I love teaching Korean students because you're so good in math. And, you know, typical American students, I have to explain the whole calculation, even in this kind of cases. Right? Okay, very good. So now we're down to our last topic today, I think. Well, evaluating normality. Right? As I said, normal distribution is very important because almost all statistical analyses are based on normal distribution. Does that mean everything is normally distributed? No. Right? But you have to convert and you have to use certain ways to be able to use normal distribution in most cases. Right? But of course, there are many cases that do not use normal distribution. Okay? But in many cases, okay, in many typical cases, we use the normal distribution. So that's, in most cases, fundamental assumption, right? When we find out any random variable and we try to analyze and we try to make an inference and we try to make a conclusion about any random variable, there is an underlying assumption that random variable is normally distributed. Okay? So the question is whether the assumption is reasonable. If the assumption is unreasonable, if the variable is completely different from normal distribution, then all the conclusion will be wrong. Okay? So the testing for normality is a very important part of any statistical analysis. Okay? All right, so we can, based on what we learned so far, we can use a few criterion to, first of all, eyeball. In other words, you can just see, right, roughly, in primitive way, to see whether the distribution is normally distributed. Well, first condition is better shape. So is the other data, numbers, observations, mound shape, or in other words, we have more distribution, more observation in the center compared to the ends, right? And whether the distribution is symmetrical. Okay? So you can, first of all, take a look at the distribution and see whether they look like normal distribution. Okay? The second condition you can use is empirical rule, 68, 95, 100% rule, right? 68%. So within one standard deviation area, do we find about 65, 68%, right? Within two standard distribution, do we find about 95% distribution, and so on. Okay? All right. Interquartile range. You know what interquartile range is. Okay? That's the range where you find about 50% of the distribution, right? So the center, middle 50% will be between this, first quartile and third quartile, which is interquartile range. Okay? Or you can check some charts and graphs and construct a stem and leaf display or box plot and look at whether the distribution looks like normal. Okay? But it may not give you clear idea whether it looks like normal, but can we consider really this is normal? Okay? So these are, again, just the first stage, just rough look at of the data points, right? And then you can check some descriptive summary measures. I think I showed you how to do descriptive statistics in Excel. Let's see. And here's one variable here. Let's say return 2008, right? It is already selected, so I can go to where was it? Where's the data analysis? They changed the system here. Oh, God. Okay, let me see, data. They used to have data analysis here, so that this means, I think they went back to 2007 or something. 2000. Okay, God, that doesn't. So I have to do, I think, option here, and additional function, and go here. Okay, you have to check data analysis here, and let me see. Is it? Okay, now I see the data analysis here. This is bad. Why do they change the system? Okay. All right, so we go to data analysis, and 기술통계법. That's descriptive statistic, right? Okay, and okay, you have to highlight the whole thing anyway. Okay, and all right. How about right here? Uh-oh. Okay, okay, so here, check here. That's fine. All right, so this gives you some good ideas about the whole distribution, right? So first thing you can check here is if it's a normal distribution, mean and median and mode should be equal, right? That's one characteristic of normal distribution. So mean is 1.32, median is 2.6. That's quite different, I would say. And mode is 6.9, right? So that's probably bad sign, right? This return 2008 is not normally distributed, right? You can probably say that, right? Anyway, so that's what you can do, right? You can check all this, okay? Is the range approximately 6 sigma? So go back to the here. The range, there is a minimum, the distance between minimum and maximum. So that's about what, 46, 47, right? And sigma is 7.65, right? So is that about 6 times? If you 7.6 times 7 would be about what, 39 or something like 39 or less, slightly less than 40, right? And the range is about 46, 47, right? So, yeah, it doesn't really fit the normal distribution criterion, okay? You understand what I'm doing, right? Okay. Okay, good. So you can check the descriptive summary measures to see these facts. Okay. Again, you can check these things based on the empirical rules, right? Empirical rules within one standard deviation area, 2/3, which is about 66, 68%, right? Within the 2 standard deviation, about 95%, right? So, but if you have your computer available, I would suggest you always check the normality plot, normal probability plot. And that's one of your homework problems due next week, right? Constructing normal probability plot. So I'll show you how to do that. I think we have enough time. Okay. Oh. Can you distribute this? Thank you. I changed one slide. The next slide that you have on your note will be slightly different from this. So I have printed this out. So instead of the slide that you have on your note, use that one. Okay? All right, so the first thing you do, well, the whole idea of normal probability plot is this. We have our random variable here, x. Okay? And we want to find out, well, it may not look exactly like this, a random variable. May look like distribution, actual distribution may look like this. Okay? And we want to test whether we can consider this distribution normal. Okay? So we want to compare this to actual normal distribution, z distribution. Okay? And let's say we have, well, to make it simple, we have 10 observations here in this distribution, right? So we have 10 numbers. Okay? And we divide that into 10 sections, actually 11 sections. What I will explain why. Okay? But we find the actual distribution may not be this evenly distributed. This may be the first number. This may be the second number. So x1, x2, x3, x4, and then x5, right? So the actual numbers may not be evenly distributed. Okay? And we want to find out, well, we convert these numbers into rank. Okay? So this is the first number, second number, third number. Okay? And find the z-score, which corresponds to each number, right? And then we divide the z-score. We calculate the z-score with for each the same rank, right? 1, 2, 3, 4, 5, 6. Okay? And if this actual distribution is pretty close to normal distribution, standard normal distribution, right? Then there should be one-to-one correspondence, a one-to-one relationship, right? So let's say z-score for the first observation here was negative, say, 3.1, right? But if you calculate the z-score when you have the 10 numbers distribution, we can find, say, z-score maybe negative 2.9, and so on. Okay? So final step of this normality plot, normal probability plot, is plotting z against x, z-score against x. Okay? And whether there is really straight proportional relationship between the two. Okay? If x variable is, let's say, perfectly normal, if x variable was perfectly normal, then we're going to have perfect straight line, okay, between z-score and x value. Okay? If it's very weird, the distribution is not normal at all, right? Then this distribution will not look straight, either this way or this way, right? So by looking at the linearity of the scatter plot between x and z, we're trying to find out whether distribution of x values are similar to normal distribution, normal distributed values, okay? That's the whole idea of normal probability plot. Okay? So the way you do it in Excel is, first of all, you have to arrange the data into ordered array. Let me open up this file. Okay. Okay. So I copied return 2008 variable here. Okay? And as you see, they are sorted from the smallest number to the largest number. Okay? In actual data, you don't have the sorted value. So make sure first step is sort and make an ordered array of this variable from smallest to the largest. Okay? All right? And the next step is find the z-value corresponding to the order of each observation. Okay? How do you do that? You look at the next slide. Where is the next slide here? Okay. So here you should get the idea. Okay. Create 3 columns. Okay. You can change, you don't have to use the exact column name, but rank, proportion, z-value. Okay. And rank, you start from 1 to down to the total number of observation. Okay. So in this particular data, we have 180 observations. So you would go to X. Let me just recreate this here. You type rank, and you start from 1, 2, 3, and then highlight those numbers and just drag it down to 180. Whatever the number, oops, okay. Whatever the number your data observation is, okay? All right, then, okay, let me, the next column you type proportion, whatever, for you, only you need to understand this, right? And you give the formula, it is equal to this rank divided by 181. That is n plus 1. You need to do n plus 1 instead of n, right? Why? Because if you do just n, see what happens. Suppose I used 180 here instead of 181. Okay? And then you just copy it all the way down. Okay? The last score will be 1 in that case, because obviously this rank is 180 and you divide it by 180, you get 1, right? Then there is no way you can calculate z-value. Okay? We're trying to find the z-value. The next column is whatever number we came up with this proportion, right? We're going to try to come up with the z-value that has the same proportion to the left, okay? And this proportion is 1. 1 means entire area, okay? What's the z-value that has entire area, 100% to the left? What's the z-value that has the area 1, right, to the left of that number? Huh? Infinity, yes. Right. So if you actually type, the next step here, the next column is, all right, let's say z-value or z-score, and you give the formula equals N-O-R-M-S-I-N-V, I believe, norms I-N-V. That's the formula to find z-score, which has this area, and you highlight, click here. Okay, so that means that particular z-score, which has 0.005556 to the left of that number, is negative 2.539. Okay, so and you just copy the whole thing all the way down, right? And see what happens at the end. Yeah. Right? You got an error message here, right? There's no such thing. Okay? If you use 180 instead of 181, right? So let me change to 181. Just n plus 1, whatever the n you have. Okay. And back to, all right? And then we have solved our problem, right? So now the last proportion is 0.9945, okay? And Excel can calculate the probability for that particular z-score, okay? All right, so you need to do these simple steps. Okay? So create 3 columns, rank, proportion, and z-value. Okay? And then right next to it, you copy your actual variable, but make sure this variable is sorted from the smallest to the largest number, right? And then all you need to do is insert, scatter, okay? Oops, oh, I have to, come on, I didn't even select it. Okay. All right, let me just highlight these 2 columns first. Okay, and then say insert, scatter. There we go. Okay. So on this graph, what's at the bottom here, from -3 to +3, that's obviously z-score. Okay. And on the vertical axis, we have expense ratio, right? And what do you think? Does it look like a straight line? I would say no, okay? Because obviously there is one observation here, way at the bottom, that's expense ratio is negative. How is expense ratio can be negative? And here, obviously, it's not the straight line, way deviation from the straight line, right? And yeah. Come on. Oh, well. How do I get this? I'm trying to cut it out, right? Anyway, so this is another graph for return 2008, okay? And we already checked that this is not a straight line either, okay? But in reality, you know, when we are dealing with actual variables, okay, it's probably impossible, I mean, very highly unlikely that you will actually get a very close straight line. So it depends on kind of analysis you are trying to, or test you are trying to do. Some tests are robust. Robust means you don't have to satisfy all the assumptions, all the conditions, okay? And the test conclusion, test result is still valid. That's what we mean by robust, okay? So depending on what test you run, okay, you know, in a few weeks, couple of weeks, we'll start talking about the hypothesis testing, right? We can talk about z-test, t-test, and, you know, other tests, okay? Especially t-tests are considered very robust, okay? And that means your population, underlying population, doesn't have to have real normal distribution, okay? So in reality, there are some room for maneuver. Okay? You don't have to have exact straight line, okay? And in reality, in my research experience, if you have normality plot like this, then you can say, well, they look like pretty normal, right? Yeah, that's in real research case. Okay? All right, any question about how to construct the normality plot, normal probability plot? Okay? All right, why don't you try that at home, and you'll need that for your homework problem. Well, I'm not done yet. Hold on. So once you construct a normality plot, what you're looking for is this kind of straight line, approximately linear, right? And if you have this kind of plot, if you have some concave downward, okay, that indicates left skewed, right? If you have convex downward, I think in our case is, let's see. Yeah, you can say this is more concave downward, and this is more convex downward. Do you understand what I'm saying? Concavity and convexity, right? Okay. Then it indicates that values are right skewed. Okay? And if you have this kind of shape, you got a problem. It's a weird shape, right? Another thing you can do is, based on 5-number summary, you can construct a box plot, okay? And you can clearly see this box plot is left skewed, right? It's got a long tail on the left-hand side, okay? And you cannot, you can conclude that, this is not considered normal, and so on, okay? And here, a couple more slides. Yeah, this is an example of that same variable return 2008 analysis that we did using descriptive statistics just a few minutes ago, okay? And this is actual normal probability plot they constructed, okay? So based on all those things, we can conclude this. All right? Any question? All right, so we got just a couple of things to talk about in the next class in this chapter, uniform distribution and exponential distribution. Okay? We can finish it on Tuesday. All right? Okay, I'll see you next week. Continuous random variable distribution, and the characteristic of uniform distribution is that it has minimum and maximum value, say A and B. So any random variable x can take any number between A and B. And because x is continuous, this equal sign doesn't make any difference whether you include the equal sign here or not, right? Because when you're dealing with a continuous random variable, the probability that it will take any one single particular value is 0. Okay? All right, so minimum value is A and maximum value x can take is B. But the probability that you will find x at any single point between A and B is equal. So all the values between A and B from A to B are equally likely. That's what the concept of uniform distribution. Okay? And outside this range, if the variable, the probability that the random variable will take any value outside A and B is, of course, 0. Okay? So graphically, if you think about the probability density function, let's say 0 to infinity, okay? Let's say we have A and B here, okay? So inside A and B, the range from A to B, the probability is the same. All the values between A and B are equally likely, okay? But outside outside this range, the probability is 0. There is no chance that the random variable will take any value outside A and B. Okay? Well, we can do a little more specific. We can say a little better than that, right? If this is the probability density function, we can find exactly the functional form, right? Fx within A and B, the range is 1 over B minus A, the maximum value minus minimum value. Okay? And we can easily prove this because, well, if this red line is a probability density function, the total area under the curve or under this straight line must be equal to what? 1, right? Because it's probability density function. We talked about it when we were dealing with normal distribution. Okay? So then we know this distance. What's the length of this line here? B minus A, right? So whatever, fx, this height is, that's fx, right? Times b minus a is equal to 1. Okay? So fx is 1 over b minus a, right? That's how we obtain the height of this probability density function. Okay? It's a very simple function. Okay? And we're going to use some examples later in a few minutes to talk about possible application of uniform distribution. Okay? Well, how about mean and variance or mean and standard deviation of this distribution? Well, obviously mean is right here in the center. So it is A plus B divided by 2. That's the average between A and B. That's the mean value. Okay? The standard deviation can be obtained doing some calculations, but it is also a simple function. It's B minus A squared divided by 12 and square root. Okay? Square root of the B minus A squared divided by 12 right there. Okay? So you can easily calculate the mean and standard deviation of uniform distribution. Okay? So here's an example. Just 1 second. Okay, it will get cooler now. So here's a particular uniform distribution with the range from 2 to 6. Okay? And then we can easily calculate the probability density function as 1 divided by 6 minus 2, which is 0.25 or 1/4. Okay? All right, so there's the graph of uniform distribution, this particular uniform distribution. So mean value is 4, standard deviation is 1.1547. Okay, you can quickly calculate that, right? And then, based on this distribution, what if we want to find out some probability, right, for a specific range? Okay? So if you're asking the question, what is the probability that random variable x will take the value from 3 to 5? Okay? What's the probability that it will be between 3 and 5? Okay? Well, then we're talking about this yellow rectangle, the size of this yellow rectangle. Of course, the size of the entire area is 1. Okay? So you know how to calculate it. That's the height times the base, or base times the height, right? So that's 2 times, 2 is which? 5 minus 3, right? B minus A, according to the formula. So 2 times 0.25 is 0.5. Okay? So the probability that if random variable x will take a value between 2 and 6, and all the numbers between 2 and 6 are equally likely, right? Then the probability that it will be found between 3 and 5 is exactly 1/2, right? Right? So yeah, you can easily understand that concept. Any question about exponential, the uniform distribution? Okay. The last topic of this chapter is exponential distribution. It's slightly more complicated than uniform distribution. Okay? But this distribution is typically used when we are dealing with length of time between 2 occurrences or arrival times. Okay? And this can, as you will see in exercises, this can be used in many different cases, right? And for industrial purpose or for business purpose, it has many applications. Okay? How many employees should we hire to handle the phone calls if you're running a call center, right? It has to do with the arrival time, right? How often the phone calls arrive. If phone calls arrive once every hour, right, then obviously one person can handle. You don't even need one person, right? Maybe a part-time, half-time person, right? But the phone calls arrive every 10 seconds, right? Then you will need many people to handle the phone calls, okay? All right? So here are some examples. The time between trucks arriving at an unloading dock, right? If you are dealing with some retail distribution business, like, I guess in Korea, what's the most famous retail business? 7-Eleven? Somebody mentioned Safe Zone. Is that very popular business or frequently observed business in Korea? Well, E-Mart, let's say. So I'm sure E-Mart has many stores all across the country, and they have some distribution centers, right? And I've never been to the E-Mart distribution center, but I don't have to because I work for Family Dollar Corporation in the United States. Okay? And that was about 10 years ago, right? And at that time, Family Dollar Corporation had about 7,000 stores across the United States. Oh, actually 5,700 when I was starting. I worked for the company just for 1 year. But when I was starting out, they had 5,700 stores. But they opened 40 new stores every month. Okay? It's a crazy thing to do, 40 new stores every month. Okay? So by the time I quit the company, they had about 500 more stores. Okay? So 6,000 some stores. By now, I'm sure they have probably 8,000 stores. Right? So at that time, they had 9 distribution centers across the country. Right? And Charlotte, North Carolina had number 1. That's the headquarters, and that's where the business started. Okay? So that's the number 1 and oldest distribution center. Okay? And they had 2 large buildings. One building, had many departments. On one side, they had a warehouse. Okay? And the warehouse had a truck bay. Okay? The trucks, we're talking about 18-wheeler. You don't see those trucks in Korea. I see the largest trucks are slightly smaller than those 18-wheelers. Okay? This truck has 18 wheels. Okay? And a huge container truck. Okay? And they have 50 truck bays. So at one time, 50 of those 18-wheelers can dock at this warehouse. Okay? And inside the warehouse, that's, if you have any chance, try to visit the distribution center for E-Mart maybe. Okay? I'm pretty sure you will see a similar scene. Okay? On one side, the merchandise arrive. The other side of the building, the merchandise go out. Okay? So they receive this merchandise from the suppliers, and within the warehouse, they repack and they sort out all the merchandise and where for each box should go. And inside the warehouse, it's just a conveyor belts, a maze, like a spider web of conveyor belts. And on the conveyor belts, these boxes move at high speed. But on each side of the box, there are barcodes. So as these boxes pass through at a certain point, I'm sure there are thousands of scanners, okay, barcode scanners. And depending on where this box is headed, Busan or Daejeon or whatever, right? The conveyors automatically send these boxes to the right location. So at the end of all the maze of the conveyor belts, all the boxes drop near the truck bay, depending on the location, the destination of these boxes. Okay? So it's quite automated. So human labor is very rare in these warehouses. But in the last step, what people actually do is they collect these boxes and stack these boxes and wrap with the plastic and push them into this truck. Okay? That's what these people do. Okay? So there was a headache. One of the projects I had to handle as a researcher or analyst, senior analyst for the company was, how to keep people inside, in the warehouse, because the turnover was so high. In other words, the people at the warehouse were quitting so quickly, so often. So managing the people, the human labor inside in the warehouse was a headache. It was so expensive because it was so high turnover. Every time you hire someone, they quit within 3 months. So you have to hire new people. And training is very expensive, okay? Because when you hire new people, these new people are not very productive. And then the existing workers have to train the new workers. Okay? So existing workers lose their productivity, right? So the hiring new employee is very expensive. Anyway, it's a long story. I can tell you many interesting stories about that. But figuring out how many people to handle, how many people to man this truck bay can be an application of this exponential distribution. The time between transactions at an ATM machine, okay? ATM is an automatic teller machine that's automated bank machine. I guess in Korean it's called the 현금 인출기. Okay? So it may be an interesting thing to know for a bank. Okay? Time between phone calls to the main operator. Again, as I said, in the 4 call centers, this is a very important information to find out. Okay? All right. Exponential distribution is defined by a single parameter. Its mean value, lambda. We use a Greek letter lambda to denote its mean value. So average arrival time. Average occurrences, actually, within a certain time limit. Okay? Or it doesn't have to be time. It could be within certain location, right? How many these incidents happen within certain location, okay? So within certain distance, you can say, okay? So the lambda is also called the rate parameter. Mean or average occurrences. In some cases, this is called the rate parameter. Okay. And all you need to know to calculate the exponential distribution is lambda. Okay. All right, so actual formula, the probability that arrival time will be less than x. Again, whether you include equal sign or not with that less than sign, doesn't matter. It doesn't make any difference. Okay? So arrival time is less than x is 1 minus e to the power of negative lambda times x. And you know what e is, and so on. Okay? So when to solve this kind of problems, you would need a calculator that you can handle this, the power, right? Okay, here's a slide that you don't have in your note. I just included as an illustration. Okay? So as this slide says, the exponential distribution depends one single parameter, the value of lambda. So depending on lambda, okay, lambda value of 0.5, 1, and 2, the shape of distribution is like this. Okay? It is skewed to the right, and it just declines as the value of x increases. Okay? And if the lambda value is 2, it starts from the 2, and it goes down and so on, and 1, 0.5, and so on, if the x value is 2. Right? All right, so here's an example, let's say. Customers arrive at the service counter at the rate of 15 per hour. So average arrival per hour is 15. Okay? And what is the probability that the arrival time between consecutive customers is less than 3 minutes? Okay? So one thing you have to notice here is if the average arrival is measured per hour, then you have to convert this time, x value, to time value instead of minutes, right? So since 3 minutes is 0.05 hours, or 1/20th of an hour, right? The x value becomes 0.05. So you have to convert minutes to hour. Okay? So the probability that x value will be less than 0.05, you can use this formula, 1 minus e to the minus 15, which of course 15 is lambda value, okay, times 0.05, and you get 5276, 0.5276. Okay? You can use calculator to compute that probability. Okay? Or if you want to use Excel, if you have a computer available, you can use this Excel function, exponential distribution, and you specify x value first, and then lambda value, and 1. Any guess what the 1 is for? The last parameter 1? Cumulative or not, right? So if you're looking for probability, x will be something like this, and lambda is 7, right? Then you would use expon this 5, 7, 0. Okay? If you're looking for this, is 1, right? You have a question? You should. Does anybody have a question at this point? Yeah? Right. That's right, right? So we are dealing with the continuous probability here, right? So whether you include the equal sign there or not should not make any difference, right? In other words, whether you specify 1 or 0 here should not make any difference, right? Well, I don't know. I've never tried. We can try later, okay? Whether the Excel is doing some strange thing, okay? Whether Excel is treating the exponential distribution as discrete random variable, discrete probability or continuous probability. But theoretically, you should get the same number whether you specify 1 or 0. Okay? When we do the exercise, we'll try. Okay? Well, looks like that's the last slide of the chapter. So we can get into exercise. Any question?